This is Precalculus Chapter 13, Lesson 1 starting on page 843. All right, so this first lesson is on basic statistics. So this whole chapter is on statistics and probability. With statistics, we study a sample of the population, and the results from that we impute to the population as a whole, right? So you think of the COVID vaccine, right? What did they do? They took a sample of the population and they tested it and decided some percentage of the population may have these reactions to the vaccine. So therefore they imputed that to the population as a whole, right? So that's why statistics is important in the medical field, because that's what they do. Probability is the inverse of that. Probability looks at the population as a whole and says, okay, well, the death rate as a whole is this, right? So if you're in the sample population of a smaller group, then that's what we say is going to happen. So you see, statistics goes from the smaller to the larger group, whereas probability goes from the larger group to the smaller group. Okay? So this lesson is on statistics, where we take a small group, study them, and we draw conclusions about the population. I mean, what better example today do we have than the COVID vaccine, right? You've all heard of it. All right, so when we gather data from the sample, the data can be in two categories. So this is for statistics. So the statistical data can either be qualitative. This is a fussy marker. Or quantitative. I'll switch markers, I do believe. Qualitative or quantitative. With qualitative, it can be divided into categories, like we have categories. Like brown shoes, red shoes, vanilla ice cream, chocolate ice cream. That's qualitative. We divide it into categories. With quantitative, it's numerical, right? It's much more numerical. Like age, right? We divide the ages into, it's quantitative. Weight, hours, anything that can be divided numerically, the statistical data is quantitative. If we can divide it into a category, then it is qualitative. With quantitative, there are two further sort of subcategories. So your quantitative data can be either discrete or continuous. Discrete is when you have a minimum number of increments. Like there's a minimum increment, okay? And really this, as I write this, it really is a little fuzzy as to how this breaks out. But continuous has no minimum increment. All right, so I'm just going to tell you, even though I struggle with this, right? Is it discrete? Is it continuous? When Thomas was younger, we measured him all the time. He went to the doctor to measure his height. And they would measure him like 3 times and then take the average. because there was this minimum increment, right? But sometimes because weight is not necessarily that way always, even though in our minds we think, well, the minimum increment is a pound, right? Sometimes weight can go up to the decimal places, particularly for people who are maybe on a diet, right? And they want to know exactly how much they've lost. They may not look as the pound as an increment, right? The best example of discrete as compared to continuous is like if we're counting cows, right? Or if we're counting people. There's no such thing as a half a cow unless we're talking beef, right? But if you're counting people, that is absolutely a discrete number, all right? Some of the other areas are a little fuzzy. All right, so look at so as I tell you that, even the way that your book looks at this is going to be a little different. Look at example 1 on page 844. All right, just as I tell you that Thomas, when he was measured by the doctor, there was a minimum increment of inches, right? They didn't say he was like 0.58, inch of an inch, all right? They even would go, even on your ruler, there's like 16ths, and there's nothing smaller than a 16th of an inch on your ruler, right? So I would say height is discrete. Your book would say it is continuous. So, that being said, here's the types of data in example 1. Let's suppose we're looking at the height of a player on a basketball team. Well, I bet because they want their height to be bigger, I bet it's probably, is it qualitative or quantitative? It's definitely quantitative because it's a number, right? And your book would say it's continuous because there's no minimum difference. It can be some fraction of an inch. All right. Look at B. The style of shoes worn by each student in a classroom. Is that qualitative or quantitative? Qualitative. It's qualitative. That's right. The number of people in each household in the U.S. Is that qualitative or quantitative? It's definitely quantitative. Is it discrete or continuous? It's discrete because we don't have a half of a person, okay? All right, I have some more examples. What about the number of questions answered correctly on a true-false test? Quantitative. Discrete or continuous? Discrete because there's a minimum of one question, right? There's a minimum increment. All right, what about the weight of an animal at the zoo? Quantitative, discrete or continuous? Continuous, even though you're struggling with that, right? Because you're thinking, well, ounces is the minimum increment, right? So height and weight I struggle with, right? What about blood type? Qualitative, that's right. All right, now, I'm going to erase this discrete and continuous because now we're going to talk about how do we display this data? How do we report the statistics? And it differs based on what type of data it is. If it is qualitative, I'm going to go ahead and write this down. If it is qualitative, we either use a frequency table, we use a bar graph, or we use a pie chart. For qualitative, we use graphs. We use what's called a histogram, which is very close to your bar chart. And then we use stem plots. All right, so we're going to talk about these. Your frequency table. Your frequency table shows the relative frequency of each outcome. Like if we were looking at the COVID vaccine, we would say, okay, what is the outcome in that sample of people that ran a temperature over the total of people in the group? That would be the relative frequency. Does that make sense? Even though that's a numerical thing. So let's go back. Qualitative. Use a qualitative example. Okay, ice cream. And I think that's one of the examples in the book. If we had 4 flavors of ice cream, right? How many people chose vanilla over the total in the sample, right? That would be a frequency table, all right? So that is example 2. Look at the frequency table on the top of page 845. All right, that is a frequency table. What does it list? It lists your options, right? What are our options? Vanilla, chocolate, butter pecan, and mint chocolate chip, right? The frequency tells us how many people chose that. So 6 preferred vanilla, 12 chocolate, and so forth. That's the frequency. That's how many people made that choice. The relative frequency is how many people made that choice over the total number in our sample. So there were 30 people in the sample, right? And 6 of them chose vanilla, so 1/5 of them chose vanilla. So what do they do with this information? They say, okay, 20% chose vanilla. This cannot be right. 40% chose chocolate, 13%, that could be right, butter pecan, and 27% mint chocolate chip. I would have thought vanilla would have been higher, but it wasn't. So what does a company do? They decide how they're going to stock a store's refrigerator, right? Freezer section. All right, so we can do it, display this information using a frequency table. This qualitative information uses a frequency table. So what do? We show what the options are, right? Then we show the frequency. Then we show the relative frequency. All right. For a bar graph is really looking at frequency and putting it on a graph with bars. So you can take that same information and display it different, right? Notice with the bar, so I'm going to draw some distinctions between the bar and the histogram. Notice with the bar graph on the bottom of page 3. So it's from the same information in example 2, but the x-axis is our options. The y-axis is the frequency, okay? Notice the bars are not touching because there's nothing continuous about it. The x-axis is qualitative. It's not numerical. Whereas with the histogram, the x-axis is going to be a numerical value. So your bars are going to touch because there's this concept of this, that there's no in-between space. Whereas these are individual categories. All right, so we can have a frequency table, a bar graph, or we can put this same information in a pie chart. All right, so how do we put it in a pie chart? Well, if 6 out of 30 or 1/5 chose vanilla, right? If 1/5 of the sample chose vanilla, then we take 1/5 of the pie, and that's what we label vanilla. So how do we get 1/5 of the pie? Do we just guess? No, we don't. What would be the angle of the vanilla sample?
Did you do 1/5 times 360?
1/5 times 360. That's right. What is 1/5 times 360?
72.
So vanilla would be 72, which is less than 90 degrees. So 72, not percent, 72 degrees would represent the vanilla section. So what do? You take whatever the frequency over the total. So you take the relative frequency and you multiply it by 360 to get that piece of the pie that represents that outcome. Make sense? So really this is tying what you've learned really up into this date, and you're just displaying it differently. Okay, so that's the three options for qualitative information. How it's displayed, how it's presented, that's what companies do, right? Or even in the medical field. They don't really use categories, but they're in quantitative. Okay, so everybody needs to look on the bottom of page 846. Okay. Does everybody know how to get this angle? You take the relative frequency, right, times 360. Okay. Now, quantitative information, which is what we use the most. All right. On the bottom of page 846, it gives the graphs. All right, so it can be uniform. So an example of uniform would be the age of a person in a kindergarten classroom. Or the age of a student, I shouldn't say because there's a teacher. The age of a student in the kindergarten class. They're all about 5, right? It's pretty uniform. So that's a straight horizontal line. Symmetric. That's where at some point it peaks, and from the left and the right it approaches that peak the same. Like there's symmetry on both sides of the peak. You see that? That's like the ACT. The peak is, for the ACT, is always hovers around 19 or 20. That is the average of everybody who takes it, right? That's why college entrance requirements are around that. All right, skewed right. Skewed right means there's a whole, skewed right, the tail is on the right. Okay, that's how I remember that. Skewed right, the tail is on the right. You see how it goes down on the right? Mm-hmm. Skewed right, the hump is on the left, the tail is on the right. So skewed right, that means the lower end is on the right. Okay? So that means there's a large population on the lower end of the quantitative scale. So an example of that would be the age of the people at Cedar Crest Elementary. There's a whole lot of young people there, and there's a lot fewer older people there. Does that make sense? That would be a skewed right. skewed left is when the tail is on the left. I just want to make sure I'm not using my examples in here. Okay, so something skewed left would be similar to like the age that somebody retires. Well, hardly anybody retires very young, right? I mean, typically you're older when you retire. So the bulk of the population that retire is going to be higher on the numerical scale. So skewed left would be like the age at which a person retires. Here's some more examples. And you tell me, I already gave this one away. I'm gonna have to think of another example. Okay, which one do you think would represent the age that a person dies in the age of death, average age of death for all people in the United States? Yeah.
Skewed left.
Skewed left, because most people are older that die, right? What would you think the day of the week of the residents in Louisiana have a birthday? Huh? I think it would be uniform. I think there's as many people that have a birthday on Sunday as Monday as Tuesday. It's probably pretty uniform. Okay, here's another one. It just came to my brain. The age at which a person gets their driver's license in Louisiana. Yeah.
Skewed right.
Skewed right, because they're definitely younger. There's fewer older people. Like there's this none at the very early ages, then there's this big at 15, 16, 17, 18, and then a great decline and the tail goes on. Yes, so definitely skewed right. What do you think about the grades of people in sequitur? Like grades, SCL. That. What do you think that would be? I think it's more symmetric, yes. So that, everybody about a CH, right, or MCH, right, and then out from there. So I think that is much more symmetric. Okay. So there's this word on the top of page 847. It's called an outlier. An outlier is something that is so far different from the population. Like here would be an outlier in my subdivision. Most of the homes in my subdivision are about the same price, right? Give or take a few $10,000, right? I mean, they're pretty much all the same price. Until you get to the very back of my subdivision, then there are a few homes that are very pricey. They have lots of property, they're bigger, and they are much more expensive, right? So those homes are outliers in my subdivision, right? If we're looking at the death rate, the average death rate, an outlier would be like an infant passing away, right? So typically, to represent statistical data, outliers are removed. And we're going to talk about that when we come to computing the statistics for the quantitative data. All right. So, example 5. You have to choose. Which one is it? Is it uniform, symmetric, skewed right, skewed left? Hopefully I haven't used all of the, well, I think I've used C. Okay. A, the last digit of each number in the phone book. What do you think that is? Do you think it's symmetric? I think it's uniform. I don't think one number is chosen any more than the other. Right? I don't think like there are more 5s than any other number. I think they're pretty much symmetric. The salaries of the employees of a corporation.
Skewed left.
Okay, skewed left would mean a lot of people. Okay, let's think about this. Skewed left would mean a lot of people make not much money. Few people make not much money, but a lot of people make a lot of money.
Could it also be skewed?
I think it's skewed right because I think the majority of the people in a corporation make a lower salary and only the CEO, the VPs make big money. All right, we said the age of retirement. What was that? The age of retirement is skewed left. That's right. What about the heights of all adult women in the U.S.? I think it's more symmetric. So I think there's this average height, I don't know, maybe I'm average 5'3", 5'4", 5'5". But I also think there are as many people shorter as there are much taller, right? I think that probably is a little more symmetric. All right. So graphs. We can represent data with graphs. So I'm going to jump down to stem plot. I put histogram right by bar graph because they sort of relate. They sort of look alike. Your book goes from graphs to stem plots because really a stem plot is like a graph laid on its side. So really if we took this and just laid it on its side, then it's a stem plot. Look at, okay, so you probably don't even remember stems from Algebra 1. That's probably how long it's been since you've actually done a stem plot. But with a stem plot, it's like the stem and leaf. Okay, that's what they would have called it. You have a stem, right? And then you have a leaf, even though they're not calling this in your book. All right. So your leaf is always one digit. It's the smallest digit, and everything else goes to the stem. So if I had 104, 105, 103, 104, 100, no, let's get out of that, 11, okay, I'm just making up numbers, right? All right, if I were just going to take those numbers and put it on a stem and leaf plot, I would not write stem leaf, but you get the idea. So my 2 digits would go to the left, and 10 is the smallest. Then I write it numerically. I do repeat 4, 4, 5. Make sense? Then I do 11, 3, 4, 5, 6. So if I look at the stem and leaf plot and I draw my graph here, then I say, I didn't intend for this, but it's uniform, isn't it? Because if I turned this, rotated it 90 degrees counterclockwise and drew a line, it's uniform. If my numbers would have looked like, let's just say, I'm just making something up, right? Then this would be more symmetric, right? Or if my numbers looked then this would be what? Skewed right. So actually your stem plots and your graphs really are just rotation's 90 degrees. You could tell the difference, right? All right, so they have done a stem plot for a set of data on the bottom of page 847. And I just showed you how to create one, right? Look at example 6. You always only have one digit on the left side of the line. So, for example 6, the only number that would be on the right of that line, or would be considered your leaf, is the 10th place, the number after the decimal. Your whole numbers would be to the right, and they have done this. So look at the solution right under example 6. So what would you call that graphically? What is that data? Skewed right, because if we rotated it, well, of course it's gonna, if I drew a graph, it would look like this. The high part would be initially, and the low part would be where it ended. My iPad won't let me do that. All right, does that make sense? All right, you can do the same with a histogram. Look at example 7. Actually, go to page 850, and they've got a histogram for you. Okay, do you see the difference between the bar graph? See, these bars touch, right? So in this histogram, figure 13.1-4 on page 850, between 150 up to 200, but not including it. You see, even though that bar goes down at 200, that means it doesn't include it. So that first category on the x-axis is like 150 to 199. That's that first bar. The second bar would be 200 to 249. That third bar would represent the frequency, how many people from 250 to 299. So I would say from 150 to 199 is probably 1. Same for 250 up to 300. And then, on from there. Does that make sense? So really all you have to do is have the numbers, and you can represent them differently. Your histogram would also show you how the information looks graphically. So that information on that histogram, what would you call that graphically? How is the data? What would you call that?
Symmetric.
I would call that symmetric, because there's this peak in the middle, then it goes back down. It's more symmetric than anything, than any of the others.